Thank you very much. So pleasure being here. Yes, initially, as we discussed, we wanted to talk about cybersecurity. But if you talk about cybersecurity, I need first to make an introduction about what do I have to protect? What are the assets do I have to protect? So, and then this would become a small introductory presentation to CERN. And given the time constraints, we came up with the idea to split this into three. We will discuss today the engineering feats to bring a Large Hadron Collider underground and in operations. Tomorrow we'll talk about the cybersecurity stands and measures we have to apply to protect the accelerator, but also other computer centers at CERN. And on Wednesday we will just discuss about cybersecurity for control system, which is my origin. And I will just rant about how shitty the whole situation with control systems is. But for today, let's start very simple, talking about CERN. The contents of the presentation is in principle very simple. I will start talking, how can I get rid of this here? I hope this is working. I would like to start with the riddles of Mother Nature, giving you a very, very small, quick introduction into particle physics. Before we then discussing about the Large Hadron Collider, and I give you some instructions how you can build your own accelerator in your garden. We discussed a bit about big data analysis, and last but not least, there's much more than Large Hadron Collider, and I will give a very, very small glimpse about what are the other projects running at CERN. But starting with the standard model of physics, it is in principle very, very simple. If you look back in time, the old Greeks, Aristotle, something like 400 years before Jesus Christ, was considering that the earth is made up out of four different matters. It's fire, water, air, and earth. And it worked very, very well for them until the 19th century, where Mendeleev came up with the periodic system of particles, which I just depict here in the slide. If you look at this, over the time, this evolved, and it became quite messy. If you look how many different particles we have, how many different atoms we got, starting with hydrogen, up to lead, and even uranium. And this is not beautiful, this is not simple. And Mother Nature usually tries to make the things simple and beautiful. So a little thinking about this periodic table of elements, Niels Bohr in 1930 came up with, look here, I just don't need to have all the atoms. If I just take electrons, protons and neutrons, only three particles, I can make them all up. So I have three particles and a set of rules how you can put the particles together, and I can explain the whole periodic table of particles there. That was a very, very good basis, and there were even some people saying, look here, physics at that moment stopped, there's nothing new to discover. Unfortunately, this is far away from the truth, because over the time, more particles were detected. So we got protons, neutrons, electrons, we got some heavy electrons called muons. Then there was the discovery of something like quarks, and more particles came up. So in the end, you have a small booklet here, the particle physics booklet, which is listing thousands of different particles. And again, we're coming back to Mother Nature. Mother Nature is simple, Mother Nature is beautiful. So thinking about this a little bit more, about the particle zoo, you can now make up the atom into the nucleus, where you get the electrons, protons, and neutrons. And inside the proton, this is then the atomic model revisited. You have something which the physicists call quarks. The proton is made out of, you can see it here, out of two up quarks and one down quark. And again, Mother Nature is beautiful. We just need to have 12 different particles. You know the electron, which is here. That is the one which is familiar to you, giving you the electricity and me the possibility to talk to you. There's the down and the up quark, which makes out protons and neutrons, and this makes up the matter which we all know. And then there are some more quarks, strange, charm, bottom and top. You can try to memorize all those names. They do not really matter. 12 of them are there in total, plus 4 different forces. The force which is very familiar with you is the gravitation. We will not talk about gravitation today, but gravitation is one of the forces which keeps the Earth together. The other force which you know is the photon, the electromagnetic force. This gives you electricity, magnetic fields. Then there's the weak force, which gives you radiation, radioactivity. Might not be too fancy, but still this is existing. it's important for the radioactive decay of particles. And this is also important for the functioning within the sun. And last but not least, you got the strong force. This is the one which keeps the nuclei, the atomic core together, and this keeps the protons together, and this kept together by particles that are called gluons. So this is the standard model. Why is the standard model beautiful? Because there's a huge predictive power. Here's the standard model basic formula. I will test you later on today to memorize this formula, but with this formula, you can explain more or less the whole subatomic world. I'm giving you an example. Here in colors are measurements of different experiments, and you can see the small thin lines which are going through each of the little symbols. This is the theory based on the formula I showed you before. And what you can see here is that the theory and the measurement very, very well fit together. And this is the beauty of the standard model. It has a huge predictive power. Not going into details, what CERN wants to do is understand the riddles of Mother Nature. We would like to go back in time from today, 13.7 billion years ago into the past, to a point which the astronomers call the Big Bang. And there are proofs, if you look tonight in the sky, there are proofs that there must have been something like a single point in time where the universe was starting to blow up. This they call the Big Bang, and at CERN we would like to reproduce the conditions right after the Big Bang. Technically, we talk about something like a nanosecond after the Big Bang. We can produce the same energy densities just right after the Big Bang. Of course, not the total energy, because if we can produce the total energy, we would destroy the universe. And I still have a good sense of living, and I don't want to see this universe destroyed. So the basic questions are, what happened right after the Big Bang? What were the rules of Mother Nature at this particular time? If you look a little bit in the sky, you can look back into time. Look at the sun. What you see happening at the sun at the moment is 8 minutes old. If the sun is disappearing now, we still have 8 minutes of light before the sun is really going out for the Earth. If you look for the next star, Alpha Centauri, it's 4 light years ago. And what you now see is the physics on Alpha Centauri and the physics of the sun. The formulas are exactly the same. So we can extrapolate back to other stars, other galaxies, looking back into time, because the light is taking some time to come to us. We can deduce that the physics laws all apply constantly over time, including the Big Bang. And we'd like to understand what happened at the time. What is the universe made of? If you just look again in the universe, in the sky, everything what is shiny makes only up 5% of the universe's mass. There are 95% of things which we do not completely understand. Dark matter, dark energy, we like to understand better what is the universe made of. And in principle, at the beginning, it was something like matter and antimatter were produced at the same quantities. This is like having money and debt. Somebody, if you have money, somebody else has debt. And the same thing is the universe. But the antimatter is not there anymore. It's gone. And again, we can discuss later where the antimatter is. We don't know. At least there is no part of this universe which is filled up out of antimatter. And again, I can discuss this if you ask me the question, why is that? How do we do this? We have a mankind's endeavor, lots and lots of physicists, researchers, technicians, engineers in electronics, in high power voltages, in cooling, in cryogenics, working at CERN. It's a mishmash, a melange of technicians, engineers, and physicists coming up with how to do it. In principle, every country on this map is sending researchers to CERN to contribute to this research. So what do? We need to build an accelerator. So let's build an accelerator from the very scratch. What do we want to do is we like to have particles which are accelerated very, very fast. So what we do is very basic. If you want to understand how your mobile phone is working, please wait with this, but if you want to understand how your mobile phone is working, take it into your hand and smack it against the wall. If you smack it against the wall, you can see what's inside your mobile phone. This gives you a very, very good hint how your mobile phone might be working. Of course, you can't do this too often because your mobile phone might be broken down. And then, of course, you're in a very shitty situation. So what we do is we take 2 protons. We smack 2 protons together with very, very high velocity, with very, very high momentum. And when we do this, in principle, what we produce is energy on the spot. And the energy density here only depends on the speed of the protons. The faster you go, the more energy you put on the spot. And if you do it really, really fast, then you produce energy densities which are something like 1 nanosecond after the Big Bang. So that is what we are supposed to do, smacking protons together as fast as possible we can to give Mother Nature a budget of energy to reproduce exactly the same thing she's done already during the Big Bang, to do and apply the same physics as she's done 13.7 billion years ago. Smacking two protons together is a little bit a complicated feat because you really have to target well. So what we do is we put all those protons into bunches. We get something like 100 billion protons in one bunch, and we chain the bunches up in something which I call a beam. There are 2,556 bunches within the beam, and what we do now is what Ghostbusters told us not to do. We cross the beams, and when the beams are crossing, the bunches are crossing, and the likelihood that one proton is smacking into another is something like 4,000%, which means that on average we have not one collision, something like 20 to 60 collisions in parallel, and that is later on a small problem to fiddle out which part of the collision belongs to which pair of protons. So this is how my home area is looking like. On the right-hand side, you see the airport of Geneva. In blue, on the left-hand side, you see the Jura Mountains. My house is not on that map here. In blue are the different sites of CERN. The main triangle at the bottom. This is the main site of CERN. You got also the northern part of CERN where we get other experiments. And embedded in this, we got the Large Hadron Collider, where the bunches, remember the 2,556 bunches, are circulating. And just to give you an idea, we are faster than the Formula 1 car. We're doing 11,000 turns a second. Problematic is, on the right-hand side of this picture is Switzerland. On the left-hand side is France. So those particles are crossing twice every 10 microseconds the border, and there must be passport controls. Actually, there are no passport controls. But this is how it's working. The distance between two bunches is 25 nanoseconds. This number will come again. And in four points, we cross the beams, we collide the protons with each other, and this is then the point where we create collisions. And every 25 nanoseconds, we create a collision, which means every 25 nanoseconds, we simulate energy densities which are coming close to the energy density 1 nanoseconds after the Big Bang. So this is how an experiment is looking like. Here's another one. We will go into more detail during the talk. So how is the cycle looking like? People usually ask, so how is this working? Here's a graph of the standard operation cycle of the LHC. It's not so complicated. It looks complicated, but it is not. On the x-axis, you got the time starting at 11 hours, 22 minutes, and ending at 1722 minutes. In blue and in red, you see the amounts of protons we got in, so more or less equivalent to the 2,556 bunches. And on green, you got the speed. So let's start. Let's do the injection. Now we fill in protons into the accelerator such that every single bucket in the accelerator is filled by protons. This costs us something like 15 minutes until 2,556 bunches of protons are filled in. Once this is done, we have to accelerate the whole thing. This takes a bit longer, 28 minutes. This is when you take your car. So first you get your family in the car, it takes 15 minutes. And then you speed up your car. I'm coming from Germany. We can go to infinite speed on the on the Autobahn. So, and the same thing is happening here. Of course, technologically, we're limited with some upper speed, and my car is also limited to 250, so I can't get faster. I tried, but it's not working. So here it's taking 28 minutes. So we are at the flat top, where we are now at maximum speed. Now the next step is we are focusing down the bunches to a very, very small size, so we can squeeze the beam, costs us 5 minutes. So the diameter of the beam is smaller. If the diameter is smaller, the collisions are much, much more. And that is the moment then where we're starting to declare luminosity. This is where the collision is starting. And this is usually something which is taking 12 to 20 hours. So 12 to 20 hours, we let just particles collide. It's a permanent production, 12 to 20 hours, every 25 nanoseconds. We got a collision. We're taking a picture of this one. Next collision is just coming up right afterwards. So this is the data taking 10 to 20 hours. And at a certain moment in time, we decide to dump the beam. This is either triggered by the operators or by some malfunction of the equipment. And then the beam is just the beam. The protons are just being removed. And we have to ramp down our speed again. So you see that the speed is going down again. And we're ready for injection once more. So that is the usual cycle which we got there, 50 minutes of preparation to fill it again, and then we're starting this again. So this is a 24/7 project. You fill, you take data, because what's counting for us is just taking pictures of collisions, because this is how the statistics come in. The accelerator complex is looking like this. This looks like more or less the public transport in your area. We got lots and lots of different accelerators. I will not explain them all, but the whole business starts at the very, very bottom with the so-called LINAC 2, LINAC 3. This is where we start accelerating the protons to 30% of speed of light. Then they're getting into the booster. I hope you can see my mouse pointer here. Going into booster and we'll be with 90% of speed of light. The proton synchrotron, 99% of speed of light. Then it's getting into the SPS, and now we're talking about energy. This is something like 450 GeV, whatever that means, and later on in the LHC. So it's a 5-stage approach. The same with your car. I think you never manage to start your car in the 5th gear and speed it up to maximum speed. You need to have you need to have your gearbox and going to the 1st gear. So this is where the origin is. Here is where we start with all the protons. It is just this little red flask here with hydrogen. Hydrogen has more or less, it's a proton which is circulated by an electron. Very simple and such. And this hydrogen is put into this very, very little oven, which is marked as a proton source. Here's the oven. And if you heat up the hydrogen hot enough, it's becoming a gas. And if you heat it more, it's becoming a plasma. And a plasma is protons and electrons, which are dissociated. So you have protons and you have electrons, but they're not paired anymore to combine to an atom. But there's now a soup of protons and electrons. And if you apply to the soup now, on the right-hand side, electric field, which is positive, the electrons tend to go there. If you apply to the left-hand side, an electric field which is negative, the protons tend to go there. So that is the first acceleration the protons see. They're attracted by the negative side and are escaping to the small nozzle, which you can see on the right-hand side on the picture. The first acceleration is done there, and the proton bunches are being formed, going then into an 80-meter long so-called linear accelerator, where they're accelerated to 30% of speed of light. This is our very, very first, sorry, this is our very, very first gear of the gearbox. How is this working? If you would like to look inside, it's more or less an assembly of charged plates. Just think of metallic plates which have a hole. And every time the protons are coming, we keep a negatively charged plate in front of the protons. So they're accelerated to the negatively charged plate. But when the protons are coming closer, we switch the plate off. And just by inertia, the protons are then continuing through a hole in the plate to the other side of the plate. And once they're through the hole, we kick the plate and turn the plate up to positive charge. So now the protons are getting even a kick from the rear. And if you build up a stack now of negatively and positively charged plates, with this, then you can build up your very, very first stack of acceleration. Alternating plates, positively and negatively charged, to get up the speed. And this is done over 80 meters to come up with 30% of the speed of light. The second layer is then the proton booster. This is the best picture I was able to find. You can see more or less the accelerator here. I will skip this a little bit. It's just the second gear, because the third gear, you can see it more clearly. It's getting bigger. You can see here now the apparatuses for guiding the particles, because our accelerators are round and proton beams usually have the tendency to go straight. I think everything has the tendency to go straight if it's not held on the circular path. Just try to throw a ball, your ball would like to go straight, and only gravity is bringing your ball down to earth anymore. Take your car on ice, you can try to steer as much as you want to. Your car has the tendency to go straight. So what we need is an assembly of something we call magnets. Here you see so-called dipole magnets. Dipole magnets have a north pole, usually on top, and the south pole on the bottom. And those magnets are bending the beam onto the circular path. So every circular accelerator is built out of two-pole or dipole magnets. And in between, you can see the vacuum pipe, which is guiding the protons. It's a vacuum pipe. It's an ultra-high vacuum, completely removed of air, because we don't want to have the protons colliding with air. We would like to have the protons collide in points which we define. And this is definitely not in the middle of the accelerator. So here's the proton synchrotron. It's 600 meters long, which is the third gear of our acceleration chain. The fourth gear is now already 70 meters long, and you can see again dipole magnets in red. And here's a special magnet in blue. It's called the quadrupole magnet, which consists out of 2 north poles and 2 south poles, which is used to squeeze down the proton beam again, because protons are nasty. Remember, we got 100 billion protons in a bunch. They're all positively charged. They don't like each other. So they more or less try to blow up the beam. This is what the beam will try. It will blow up because it's positively charged. The protons would like to escape everybody, but they can't. So they are squeezed back by those quadrupole magnets, 4-pole magnets to north, to south, to squeeze the beam horizontally, to squeeze the beam vertically again and again and again. If you look a little bit farther down the tunnel, you'll see there's something like a pattern. You got a dipole magnet, you got the quadrupole magnet, which is the blue one. You got 2 dipoles, you got a little of beam pipe, and then it's repeating. Again, a quadrupole, dipole magnet, and so on. And if you go down to the tunnel and you go for a walk, then you will see this pattern repeating and repeating and repeating. I'm just checking a little bit of the questions. Sorry if I've been too far on the slide. You get the slide stack, so don't worry, Said. That will come to you. At the end of the cycle, are the dumped protons used for any experiments? And principally come back to this one, you can. For the LHC, you can't because the energy is just too enormous. You will just more or less destroy any experiment which you can put at the end. I come to this in a second. And Alan, I have no clue about the purity of the H2 source, but the deuterons and the end protons and neutrons. And I think in the initial acceleration process, the deuterons will be more or less filtered away because they're just not making it through the magnet lattice, which are just depicted here. They are just too heavy because the protons and the neutrons are attached to each other, and they have a different way of going through the magnet fields provided by the magnets here. Last but not least, last gear, here's the LHC, and yes, this is dull. You don't see anything. We'll come to this in a second. The magnets here are not normal conducting magnets because you just can't get it normal conducting. We need to put everything under superconductivity, and this means you have to put all your accelerator into a cryogenic facility, into a fridge more or less, and cooling it down by 270 degrees Celsius, down to something like 1.9 degrees Kelvin. Large Hadron Collider is 27 kilometers long. So now let's build one. Here's the easy path from IKEA. This is one way you can do it. It's not too expensive. I'm not sure if it's in your IKEA, but here you can still buy it. First, you need to have dipole magnets. As I said, we need to have magnets for guiding the beams. The beams are proton beams in red and in blue. They are separated because we don't want to collide them in the accelerator. So we keep them separated all over the path. And for each of the paths, we have a dipole magnet of something like 8.33 Tesla, just to bend the beam along its path into the tunnel. The problem with the magnets is 8.33 Tesla, you need to have some current to produce this. Think once more, you need to have 10,000 amps of current to produce an 8.33 Tesla field. This is a cable which you can use for 10,000 amps. You see here the copper connectors. You see some water pipes going in because this is heating up and it's getting 10,000 amps. So you have to water cool it. But I think we all agree with such cables here, you cannot wind them up to give you a magnet. If you don't know how a magnet is looking like, tonight go home, open up your doorbell. Inside is a small copper cable, a small copper wire which is wound up, which is giving the magnet field for this little metal piece which is hitting your doorbell. Please don't do it. Maybe I just get in trouble. I haven't said anything here, but this is the cable, how it's looking like. In shape, it's 10 centimeters by something like 4. You can't wind this up and it will get even more expensive. So what we do is we do not use normal copper cables. We use this one. Those are superconducting niobium titanium cables, interleaved. You can see the little different fibers inside, and they can take up unto 12 kiloamps. Think at home again, your cable at home might take 10 amps. So we are now something like 1,000 times the current which you're getting out of your power socket. And the cable size here is something like, unfortunately you can't see it, it's something like 2 centimeters wide and something like 2 millimeters thick. This is the superconducting cable, which is wound up here. You can see here again, the magnet which I showed before. I illustrated the blue and the red beam inside, and you can see an opening cutting of all the layers of the superconducting cable. It has 2 layers, and where the layers are not hitting is the North Pole, and below is the South Pole, and everything is put into steel plates because magnets create quite some force, so you need to keep them together, and this is done by steel plates. Everything is then, the beam pipe is then looking like this. You can see the beam pipe. It has 2 different pipes which are attached to this, the small little tubes on the left and the right-hand side. This is where we flush this with liquid helium to cool down the beam pipe, because the beam pipe itself is heating up due to the synchrotron radiation of the accelerator. If you don't know what synchrotron radiation is, maybe you should have asked the question, who of you has an accelerator at home? Somebody? Your microwave oven is an accelerator. Your microwave oven is accelerating electrons, like we do with protons. The electrons are bent by a dipole magnet, like we bend with dipole magnets. And when particles are bent, every charged particle, when it's bent, it's emitting light. In your microwave oven, guess what? It is microwave radiation. In your ductors, the electrons are much, much faster, but the X-ray machine is like your microwave oven, emitting X-rays, which is just microwaves, but more energetic. In our case, it's even more energetic, and this energy needs to be absorbed. And unfortunately, beam pipe is the closest to the beam, so the beam pipe is being heated up by the synchronous radiation from the accelerator. So we have to cool it down, and give you a size of the beam. The beam size is something like 4 millimeters in diameter, and I hope I got it here somehow right from the size of that Queen Elizabeth II coin. I think it's 25 cents, isn't it? It's a quarter, isn't it? Oh, don't blame me. I hope it's a quarter. Let's be at a quarter. Here you see the assembly of one of the dipole magnets. We have 1,232 magnets making up a circle. You can see again the illustration of the red and the blue beam. So you see the beam pipe. You can see inside a cryostat. This is the assembly which needs to be kept cold by minus 270 degrees Celsius. Because only when it's kept cold, the superconducting cable can be superconducting. If it's something with 10 degrees Kelvin, it will be normal conducting, and this will not work, because normal conducting means it will create heat, and heat is energy loss, and the magnet field is not efficient. So we need to keep it superconducting, no heat, no losses. The problem is, in the tunnel, you got ambient air temperature, 20 degrees Celsius. So the outer blue vessel has 20 degrees ambient air, and over the 5 to 15 centimeters of the cryostat inside, you got a temperature drop of 300 degrees Celsius to minus 271 degrees Celsius, or 1.9 degrees Kelvin. So the cryostat is kept cold. The big tubes, which you can see on this picture, I'm not sure if I have a bigger, better one. The big tubes are used to flush the whole assembly with liquid helium. The liquid helium is flushed throughout the 27 kilometers of the accelerator, throughout the 1,232 dipole magnets. And when you flush it enough, you keep this cold. And once it's cold, the superconducting cable is cold, and we can start powering the whole thing. The magnets have been tested. Here you can see a testing facility at CERN where we're testing all the magnets, whether they can be cooled down, whether we can put 11,000 amps to the superconducting cable without destroying everything. So that has been all tested. I used to mess with the magnets. So there you are. Nice to see Alan come to us. We're still looking for magnet experts. The magnets need to go underground. The accelerator is something like 100 meters underground. So here you see the transport of one of the 15-meter long dipole magnets being underground. Here it's coming underground into the accelerator tunnel. We got a little train, which is then bringing the magnets to its final place. So you can see how the magnets are positioned. 1,232 need to be aligned. The positioning is not random. First, some magnets are a little bit stronger, some magnets a little weaker. So you need to compensate for this. You put a stronger magnet behind the weaker magnet. We're just talking about something like a per mil of difference in magnetic field, but you have to compensate for this one. What you also don't see, those dipole magnets are 15-meter long, but they are not straight. They are a little bit bent by 50 millimeters sagitta, because they have to follow the size of the tunnel, and the tunnel has a curvature, so you have to take care of this. You can see the interconnection. You see again the illustration of the blue and the red beam, and now you have to solder together the superconducting cables, plus all the signal cables and everything else. Then you have to interconnect the helium pipes, so you have to make sure that the helium is flushing through, and then you have to make the insulating shielding, because everything what you see here is supposed to be 1.9 degrees Kelvin cold, or minus 270 degrees Kelvin cold, while in the tunnel you still can make your evening walk or come by with a bicycle, and you got a nice and fresh 20 degrees Celsius. So this is how it's looking in the tunnel. You can see the white line, which is used for the strain to transport the magnets to the right place. It's also used for our French colleagues when they've drunk too much wine to figure the way out again, but I haven't said that part. And this is the whole assembly, the magnet, the accelerator. If you walk there from one access point to another, which is about 8 kilometers, it's quite dull. You just see this blue pipe, and that's all you see. Not completely, you see also gray magnets. Those are the superconducting quadrupole magnets. Remember, quadrupole were those ones which are used for focusing. So focusing, and you can see this in the upper left picture, it has 4 coils to create 2 north poles, 2 south poles, to squeeze the beam. So if you want to build this in your yard, you need to have an acceleration device, you need to have dipole magnets for the circle, and you need to have quadrupole magnets for squeezing down. And you need to get the energy in, because everything here, as said, it's taking 12,000 amps. Unfortunately, if we're getting the electricity from the Électricité de France, so from the French energy providers, it comes with normal overland lines, and those are normal copper lines. So now you have to convert this. And here you see the bank where the big copper cable, they're still hanging at the wall, at the ceiling here. Copper cables are connected to, the ones which I showed you before. And then within this cylinder you see there, you have to make sure that the current is getting in from outside into the accelerator, but the cold, the minus 270 degrees Celsius, should not go out. So this is an insulation bank to make sure that the energy goes in, but the cold is not getting out. Acceleration, remember the plates which I was talking about. This is one of the standard cavities which we're using for acceleration. Usually I said we got this charged plates, positively charged, negatively charged, and you toggle this to accelerate the beam. Positively charged, switch it off, negatively charged, and so on. You can do this until to a very certain speed, but if you're getting faster, it's not working anymore because the protons, the electrons are not getting fast enough on top of the plate and going away again. It's just technically not working. So instead, we're using such a cavity. It has a certain shape, and what we pump into this cavity is a radio. It's a radio field of something like 500 megahertz, which is more or less then wobbling inside this cavity back and forth. And when it's wobbling back and forth, it is inducing on the surface of the cavity either positively or negatively charged. So it's by induction, and this you can do much, much faster, ergo with 500 megahertz. And once it's installed, you can see it here. You see on the left-hand side, the blue beam. This is the beam which is this very first apparatus, accelerators. And later on, you can see one which is a little bit set aside. This then for the red beam to be accelerated. It's just done in one single point. This is the advantage of having a circular accelerator, because the beam is coming back to get accelerated again and again and again, 10,000 turns a second. So we have 10,000 times to accelerate the beam over 1 second. This is how the people were looking like when we had the whole accelerator built up the first time and we were ready to inject the very, very first proton. I'm standing somewhere in the rear, but think of this once more. Maybe you have a miniature train. You take your miniature train out on the lawn, you build it up in a 27 long circular assembly. So you get a very 27 kilometer long circle. You put your train on and you power it up. Can you imagine how happy you will be if the train is really doing the tour and one moment it's coming back? We've been quite happy, and you can see it here on the screen. Top left.
Countdown, 3, 2, 1.
So I'm not sure if you saw it. I will do it once more. That seems to be very, very trivial, but it's not. Just look at the left screens. Oh, look at the left screens. Here, just the left screens.
Countdown, 3, 2, 1.
So what you should have seen is the 2 white dots which are just appearing. What are the white dots? One of the white dots is where the beam is entering the LHC, and the second white dot is when the beam made 1 turn and coming back. So because it's very, very fast, 10,000 turns a second, they appear at the same time. For your miniature train, it's more or less, you see the train coming through once, then you wait for the 27 kilometers until the train is coming the second time. And when you see the train coming again, then you're lucky and you're happy that it made the round. And the same thing was in our place. This is the control center, how it's looking on daily times. We got 4 different islands. The island at the very rear under the CERN, on the blue CERN logo. This is the island where we do the cryogenics to keep the whole machinery down to 109 degrees Kelvin. On the left-hand side in the rear is the so-called injector complex, where we have the first, the second, and the third gear for the acceleration. At the bottom left is the 4th gear, and at the right is the LHC controls, where you control the LHC. If you want to come to CERN, Be my guest. We are doing visit tours. You can go on the balcony and can look inside and see how the whole machinery is ticking.
Dr. Lüders, if I could interject here, we have a queue of a few questions here. How often do incidents occur with these materials, as well as the high amps of electricity? I imagine safety is the utmost.
Yes, Jennifer, you're completely right. So with the materials, I will have later on an example of where one of the soldering didn't work, and this delayed us by something like 1.5 years. But usually the actuators are all, components are all tested. So the materials can sustain the electricity, which we were just talking about. So that chain is very, very, very probed. But you're right, we got lots and lots of safety systems in place. If there is a small leak of current, for example, we can monitor this. The magnets themselves, we're monitoring the temperature of the magnet. So if the temperature is changing just a little bit, if we see that it's coming close to the safety envelope, then we got machineries in place, which you call it beam dump. Remember what I said at the beginning, we dump the beam. You can do this by operator invention, but you can also do this manually by triggering, one of the safety systems are triggering. And this costs us something like about 4 microseconds or 4 turns in the accelerator. So 4 turns we need to get rid of the beam. And once the beam is gone, we have a very, very safe situation. So we get lots of safety systems to actually monitor the beam. I'm not sure if I mentioned this now, but I will mention this definitely later. Think of the beam once more. The stored energy of the beam is an equivalent of 80 kilograms TNT. 80 kilograms, it's more or less me and TNT, but squeezed down at this very, very small size. Losing the beam in the machine, in the accelerator, will destroy the accelerator. It will not destroy anything else, but it will be Star Wars. This is your laser saber opening up your beam pipe. Once it has opened up the beam pipe, cut open, the beam will go into the magnet. The magnets are superconducting, they are cold. The helium will see a cold beam. The helium will more or less then evaporate, increasing by a factor of 700 in volume, and then more or less break open the accelerator, the magnets, and then evaporate into the tunnel. We had this in the past, so I know what I'm talking about. So there are lots and lots of safety systems which know exactly where the beam is. If the current is not nominal, we get rid of the beam. Is the temperature not nominal, we get rid of the beam. If there's something indicating that the beam is misbehaving, we get rid of the beam. There is no risk for the environment here because it's all contained in the tunnel, but still we don't want to see our accelerator being destroyed because this takes some time. I hope this is answering the question. If not, please ask again. Other strict controls, sorry.
Oh, I think that answers that question. Second question, since the magnets are superconducting, do they require additional electricity once their field is generated?
There is some magnet field which is leaking out of the magnets. Also for the RF noise, no way to go into. Once the accelerator is being put in commissioning, there is something which is called a petrol. We go through the accelerator, we investigate, and then we lock all the doors. So there's nobody supposed to be neither in the accelerator tunnel. Remember what I said about the synchrotron radiation? You don't want to sleep under an X-ray machine, and the same is for synchrotron radiation. It will be contained in the tunnel, but you do not want to be there. So we're making sure that nobody's there. The same for RF. The RF system in point number 4, this is a no-go area when it's being switched on. So we're making really sure that there's nothing in. Electromagnetic devices, yes, that is a problem, more for the experiments than for the accelerator, but our electronics are specially designed not to be affected by electromagnetic fields created by the RF system or by the magnets. Okay, we talk about how I get rid of the beam later, and let me move ahead a little bit if you don't mind. So now we're taking data. Remember, we got the 2 collision points. Now we have to take pictures every 25 nanoseconds. So this is how one of the experiments are looking like. If you look a little bit closer, there's a small person standing at the very, very bottom. To explain you how this is working, I cut open this experiment, how this is working. On the left-hand side, you see now 1/4 of the experiment. On the left-hand side, you see the collision, and you see different layers of detective material. The first layer on the left-hand side, we call a silicon tracker because it's made out of silicon. The same silicon chip which you got in your iPhone's camera, we got the same thing, but our silicon is wound up into cylinders. You can see lots and lots of cylinder layers. and we have something like a surface of 250 square meters of silicon inside the detector. So why is this done? Think of this as a pixel detector, like your pixel camera, and each pixel has a coordinate, like a chess field, A1, B2. So now you see a particle going through, and it's leaving a trace, A1, B2, C3, D4, and so on. And later on with your computer, you can combine those different points to give you the trajectory of the particle, for example, of the green particle or of the red particle. Because the whole thing is put into a superconducting solenoid, into a superconducting magnet field of a very, very big size, and you see it later, and the particles are bent. Every particle magnetic field is bent. So now I can distinguish between the red electron bending into one direction and the green hadron here. It might be a proton or a pion, which is bending the other direction. So now I know by the trajectory where the particles are coming from, which curvature they have, and the curvature is proportional to their speed. Remember the three-finger rules of basic physics. So I have the speed of the particle, I have where they come from. The next layer is something which we call a calorimeter. After we've measured the trajectory, which is highly non-interactive because we do not want to interfere with the trajectory, now we can absorb the particles. In the electromagnetic calorimeter, we stop only photons, particles of light, and electrons. So now I can distinguish between photons and light and electrons, because the photons are neutral, they didn't leave any trace. So the upper part, where this dashed line is going, there is nothing in the detector, but I still have the energy deposition in the calorimeter, so that must be a photon, while the red line is pointing to an energy deposition, and that must be an electron. Protons, heavier particles, are stopped more or less in something which we call the hadronic calorimeter. And you can see one more. The green dashed line is something neutral, like a neutron, and the green solid line is a proton. So now I can tell you where the particles come from, which charge they have, because they are left or right bent, which speed they have, which type they are, and how much energy they had, because the energy deposition is more or less integrated over the calorimeter, and I can read this out. And there's one more particle which is very special, called the muon, that is the brother of the electron, a little bit more heavy, that is crossing the overall, and it's leaving even on the right-hand side in the so-called iron return yoke with muon chambers. It's leaving a signature there, and that is very, very handy for us. So with this is more or less the picture you're taking. Don't think that the picture is looking like this. What you're getting as a physicist is more or less a small table of the different particles, the energy, the speed, and then you have to do your analysis to combine everything together. So this takes a little bit more of work to get this done. If you look at the silicon detector, here's a photo of the silicon detector. You can see the different wafers of silicon. No, it's not one surface because it's very difficult to produce. You can see here 3 layers of cylinders, and every single chocolate bar there is one silicon detector with a chessboard. And you get connectors and cooling and power to get everything running and working. Calorimeters are more or less made out of lead. What you want to do with the calorimeter is you would like to stop the particle. To stop the particle, you need to have something which is really, really dense. Lead, for example, is really dense. So you shoot the particle at the lead, and the particle is then colliding with lead atoms, and it's being stopped. But this doesn't give us anything in measurement, because you would like to measure how much energy the particle had. And what we do is now, we have in principle a mixture of lead here, and this bars here is lead, 99% pure lead, but transparent. Why do we need to have them transparent? Think of my particle going into the lead. When it's being slowed down by colliding with all the different lead atoms, it's emitting light. And the light is proportional to the initial energy. And we can read out the light by the small Kapton cable, which is glued on top of this lead crystal. And the light is proportional to the energy. So I now have exactly how much energy the particle lost. It's more or less the same in Formula One. If you look at Formula One cars and they are breaking down, look at the braking discs. The braking disc might glow red, or they might even glow white. You might see some dust, but then they've been too fast. But by the light, you can see how fast the Formula One car is. And the same thing is what we're doing here. You can see the iron return yoke with 2 people inside, so you get an idea of the size. This is 60 meters in diameter. Inside is the magnet. Here you can see how the magnet is being inserted into the so-called central wheel, into the central assembly. In principle, what we're doing here is the magnet is put onto this yellow left-hand table, and now the right-hand assembly, this red iron yokes, are put on air cushions in orange at the bottom. You see the rails, and it's now moving on top of this, this inner cylinder of the magnet. I don't tell you any association, but yes, it's more or less the same association which you might think of. Here you can see the assembly. Again, in the rear, now you see the red iron yoke. You see in silver the muon chambers. The big circle is the magnet of this particular experiment. And on this yellow assembly, you see the hadronic calorimeter. This one is not made out of crystals. This is made out of steel plates interleaved with transparent plates. Same as the calorimeter, as the lead calorimeter applies. The particle goes into the steel plates. It's creating an avalanche of additional particles by slowing down. It comes in the transparent plate, emitting light. Again, a steel plate being slowed down. Again, a transparent plate to emit light. And with this, you can start getting an idea of the energy of the particle. So here's the overall assembly down in the cavern. Just again on size, look at the right or left-hand side. You can see the ground floor, first floor, second floor, third floor, and even the fourth floor at the very, very top. You can see straight looking into the, you're looking straight into the beam pipe, and around you can see in the middle the fully cabled inner detector, the fully cabled silicon detector. Then you can see a layer of the electromagnetic calorimeter and the hadronic calorimeter. You can see the round magnet which is put inside, and then you can see once more the red iron yoke with the muon chamber interleaved, and all the infrastructure, all the cable, and so on. All the electronics here must be radiation hard, because when the collisions are starting, it is something like radiation which you get in outer space. It is more or less destructive to electronics. So you need to make sure that the electronics is not subject to single event upset or something like this.
I have 3 more questions that have come up here.
Go ahead. Let me move one slide back.
Do you also see tau particles?
Tau particles, or the more heavy muons, in principle, they are not long-lived enough that we see them directly, but you can reconstruct them. This is usually what is happening. The same answers to your question for the Higgs. The Higgs, the whole assembly is seeing the Higgs, or say it differently, you do never see the Higgs. Why? Because the Higgs is just living very, very shortly. It will more or less decay inside the beam pipe, but you can reconstruct it from the event. So from the overall, you can reconstruct it. What is a good example? Think of me being an accelerator. I'm creating money on my bank account because this is my salary. Now my wife is coming and spending the money, but I don't see how she's spending the money because I'm buried in my office and I can't get out. But in the evening, as a physicist, I can make a measurement. And I look in the fridge and I see milk, Coca-Cola. I see some shoes. I see Lego. I like Lego. And from time to time, I see a new car. If I now make this measurement again and again and again, I can start up with figuring out the rules of my wife. The rules saying very often Coca-Cola and milk, well, quite decent shoes and Lego, and very rarely a new car. And the same is happening here. You got the collision, you got the energy on the spot. The Higgs particle is produced very, very shortly, a very, very small fraction of time, enough to distinguish it from everything else of a noise, but not enough to take a picture of it. But you can reconstruct it of the end product. Is this giving you an idea, AC? I don't have the full name here. No, I should not remind you of your wife, but anyhow. The Higgs particle, most of the things here is done by reconstruction. You see the end product. It's like the police coming on scene of a car accident. They have not seen how the accident happened, but by looking where the body parts are and where the tires are and where the wheels and the seats and everything else is, they can reconstruct how the accident worked. And this is what the physicists are doing here. Are there any antiparticles produced? Yes, more or less half of the particles produced here is antiparticles, and over time they are absorbed by the experiments, and then they're more or less vanishing. Coca-Cola physics, I can't tell you, never done that. So let me continue with this a little bit more. This is how it's looking underground. Lots and lots of caverns, lots and lots of tunnels. We got 8 access points. Starting at the bottom is Atlas, is a collision point. Point number 2, left-hand side, Alice is a collision point. Point number 3, which is here, this is a point to clean the beam. Remember, the beam is protons which are blowing up. The size of the beam is 4 millimeters, but it's tried to blow up. So you have to make sure that everything what is outside this envelope of 4 millimeters needs to be absorbed. And we got some absorber material there, which is more or less coils, which can move very, very close to the beam, not intercepting the beam because it's this 80 kilograms of TNT, but it can absorb everything what is in its halo. Point number 4, this is where we accelerate. This is where the RF system is sitting. Point number 5 is at the very top, CMS experiment, a collision point. Point number 6 is where we dump the beam, where we get rid of the beam. This is our safety area. Point number 7 is again a point for beam cleaning. And point number 8 again is collisions. And with this, we made up one circle. So here we are once more. This is how it was looking when we were excavating the caverns. Engineering-wise, it is not very simple because we had a previous accelerator running in the tunnel, so we are not able to interfere with the operations. So CMS started very, very late in digging the cavern. The Atlas experiment started earlier. Here you can see the fully equipped cavern in its pure state. And then you put the experiment in. And since the cavern has been dug very, very late, all the different pieces of the experiment, the heaviest one was 2,500 tons, needed to be brought down into the cavern, and then everything is put together to give the experiment. Here you can see one more of the slices going down by 4 wires over 100 meters of distance from the surface area into the cavern, and then everything is pushed together. The Atlas experiment is looking similar components. I will not go into the details, but you got again a silicon detector in the center, you got a calorimeter around, and you got a magnet field for giving you the speed and the charge of the particles. It's always the same assembly. If you go to Triumph, which is maybe closer to you in Vancouver, they have experiments, they have accelerators, they have more or less the same concept. This is cooking, and we all cook with the same kind of water. For that experiment, we needed even to dug 2 vertical shaft to bring the material down. Here you can see we started the cavern digging top down. So we put the ceiling in at the very beginning so we can run the accelerator still underneath. So underneath this assembly is still a working accelerator. And then we dug down, and once we destroyed the accelerator, we were able to put the cavern in. You can see this cavern is even bigger. Just count the stories. You see the big blue hole. This is where the beam pipe is coming through. And you see first floor, second floor, third, fourth, 5, 6, 7, 8, 9, 10 floors, and the crane is bringing down a very small crane into the cavern for work. So here you see the crane again, building up the experiment, building up the different components of the so-called solenoid magnets, which is in the experiment. Here you see the experiment once more with a small guy standing in the center. And here you see the transport of some of the components. This is, for example, the end cap magnet, which is used in the Atlas experiment. I'm looking a little bit of the time, so I will skip a little bit of the photos, but I leave them in the slide stack for you to look at later. And I will leave also my coordinates so we can discuss parts of the photos if you want to later. Here's the CMS cavern completely completed. The only thing is on the left-hand side where the end cap toroid magnet still needs to be pushed closer to the center. The center is on the right-hand side. You can see the beam pipe, and you can see the red and the blue beam coming out of this beam pipe. And around again, you see electronics, because all the collisions, 25 nanoseconds, you get a collision, you need to read out all the photos. Just for the scale, if you look very closely, here's a guy standing at the very bottom, close to the yellow assembly. You see the guy? So that gives you a kind of the size of the experiment. This is how it's looking like. If you really look in front, you're looking into the beam pipe, and this is how a collision then is looking like. I know the girl is not there, but the rest, this is what the physicists are usually getting. One collision is producing thousands of different particles, antiparticles, protons, neutrons, muons, everything else, short-lived particles, long-lived particles. You can see some particles which energy is absorbed in the hadronic calorimeter, some where the energy is absorbed in the inner electronic calorimeter, some particles making it through in the muon system, and lots of particles are curving up in the center. This is what the physicists are getting, and now this is your car accident. Now you can reproduce how did this happen starting from 2 protons colliding. And when you do this, then you can figure out when the Higgs is coming. This is a 3D picture of such collisions. And if you look at the numbers, we have something like, I can read my own numbers because Zoom is in the way. Or I even don't know, you see it, I can't see it, sorry. Is it 40,000 data channels? I'm lost here. But more or less what we produce is 1 petabyte of raw data, which we cannot store because 1 petabyte is something like 1 million terabytes of no, 1,000 terabytes. So this is 1,000 hard disks a second. We just can't store this. So locally to the experiments, we got a computer center of something like 3,000 data acquisition servers, which filter down the amount of data to something like 10 gigabit per second stream, which is then going in our computer center. And I will discuss about this tomorrow. So we get something like a raw rate of 40 petabytes of data per year. Let's check the questions. So where I'm starting, I'm getting the comments here.
Supersymmetry,
looks like a
I
bust.
believe.
Do I think that the successor of the Large Hadron Collider will ever be built, even if supersymmetry looks like a bust? And the question is, the other question, how do we convince governments to invest in such massive projects? In principle, I'm not sure if we will ever build something bigger than the LHC. On the other hand, we are mankind. We are curious. We like to understand more. This is how America has been discovered, because Columbus thought, yeah, let's go the other way around. So if nobody sponsored Columbus, you wouldn't be there where you are. So this is how mankind is working. If you ask me whether any of the physics bring us further, no, nobody cares about the Higgs. This doesn't bring anything further down. But the cryogenic installations here are now used in industry. Particle accelerators are used in industry for cancer treatment, for example. Antimatter cancer treatment is something which we develop, and this might make it to light in your hospital somewhere in the future. All of the engineering documentation here has been stored in systems which we need to share with our worldwide community. In Fermilab, in Vancouver with Triumph, how did we do this? We just had a small protocol developed, which we called HTTP, or you know about this is the World Wide Web, invented at CERN to exchange information. This is fundamental research. CERN had touchpads, like the ones which you now have on your mobile phone, in the 70s to control accelerators. So it's fundamental research. We do not know what's coming out of this, but everything what we do here becomes applied research on a certain way, in one way or the other. So even if there's no supersymmetry, there are still riddles. We still don't understand Mother Nature completely, so there are open questions, and those open questions I think we still should answer to come closer to the understanding of our world. How to convince governments? How to convince you? How to convince you that fundamental research is important? Because if you don't do fundamental research, without fundamental research, you can't have applied science. Without applied science, you don't have satellites, rockets, mobile phones, television, or anything else. So if you don't do research, we just stay at the status quo of today, which might be acceptable, but we might have also decided 100 years ago to stay at the status quo with horses and no cars, or 1,000 years ago with only horses and fire. So make your pick. I think fundamental research is important in many areas, not only in particle physics, just to bring our research, our future further. Any specific requirements for civil engineering? Yes, lots of, Franks. I can give you another long presentation of how to dig tunnels, how to evacuate water, what do you do if you have to dig down through a water table, and so on. There were lots and lots of feats to get this done. So unfortunately, I'm running already now out of time, but be happy to stay longer and we can discuss those things later on. So contribute to the search for dark matter. Yes, this is what we're hoping, that we can still see some indications of dark matter. And there are some indications already, but it's not completely clear. So we have to wait for that one. So that's again fundamental research. We analyze the data and we would like to see deviations from the standard model, and the deviation from the standard model is an indication for dark matter. Unfortunately, the standard model is really robust and fits in very, very many corners with the measurement. So we have to see more. Let me move to the really big data analysis. I'm very quick. This is how he's called I don't even call how he's called, to find this guy in a haystack. And this is how the Higgs analysis is done. We got a web page where you can go to see the status. But more important is the amount of pictures we're taking. Every line here, it's data taken over the year. It's assembling pictures. This is how many pictures we got. We're talking about billions of pictures, which are then analyzed. The first thing is, can we reproduce what has been measured in the past? Because you need to prove that your detectors, your cameras, are working as they working properly, so they can reproduce physics which has been measured already before. This is like you taking a picture of me. If you take a picture of me and I got green hair, someone needs to prove you wrong, and I can prove you wrong with more and more pictures of me where I'm bald. So your camera is not working. We have to show that Atlas CMS are working and producing the same physics which has been taken before at Fermilab, at the Tevatron, in Chicago, in Vancouver, at Triumph, at RIG in Brookhaven, at DAISY in Hamburg, and others. So first we have to show we measure the same thing so we understand our detector. And once we do this, we can make particle measurements as those ones. And you see the blue, the red, and the pink, those are measurements made of CERN. And here's the Higgs. You can see how the data is coming in over time. In red, you see the distribution, how the theorists would expect what we see, and the black dots is the physics which we measure. And if you look closer, there is something like a hump at 125 so-called GeV on the left-hand side here. Let's zoom into that one. Can I get zoomed in? Here we are. You see this hump, and this is a statistical significance of something which is sitting there. And this is the statistical significance that the standard model is missing a particle. And this standard model is only working if you add now a particle called the Higgs particle. And if you now add the blue and the red together, you can describe again the black dots, which means that there must be a particle which we call the Higgs, which has a mass of 155 GeV to fit the measurement. So this is the measurement of the Higgs particle. You don't see one, you do a statistical analysis. And this is a very early statistical analysis. Today, the dots are still the dots, but the bars, these vertical lines, the error bars are getting much, much smaller. So the evidence that there is a particle needed to explain the standard model, the Higgs particle, has been established. And that is the discovery which more or less gave them the Nobel Prize to Peter Higgs, right-hand side, and François Englert on the left-hand side, because they predicted this already 60 years ago, but it took us some time to produce an accelerator or to produce some money on the spot, if you think of the picture of my wife, to buy the Higgs particle often enough that it gives you a statistical significance. I have to wrap up. More than the LHC. Here's a detector, which is part of CERN. It's in the bay of the space shuttle. Unfortunately, it's not flying anymore, but you see it marked with AMS. This is a detector with a silicon part, with a calorimeter, with a magnet, flying in the space shuttle. We were measuring particles coming out of outer space. So we have much, much more there. We got experiments in North area where we smack the protons into so-called fixed target experiments to see the physics there. We can smack the particles in the East area with low energy to make some physics measurements there. We can convert the protons into gamma rays or synchrotron radiation and make material science with very, very strong X-rays. Or we can convert the protons into antiprotons, antimatter, and making antimatter research. Does antihydrogen fall in gravity as hydrogen is falling? Does antihydrogen shine with this light like hydrogen is shining, which we see from the sun? We can do neutron physics, or we can do physics with ions, producing rare isotopes. And we're producing rare isotopes at CERN, for example, for the local hospitals, where you can then go for treatment with very, very rare isotopes, which are much, much more healthy than the standard isotopes which are used today. And then we're doing also research for future accelerators in different places. So I skip this, and due to our time, I'll skip this, just showing you some pictures of some of the halls. Here you can see the park of the beamlines. You can see the beamline coming from the top in the middle. This is the tube in silver coming down here, and then it's delivered to different experiments here, here, and here. And there are plenty of experiments also in this hall. The beam pipe is coming through here, going into this experiment to produce antimatter and to analyze the antimatter. It's the so-called antimatter facility. We're doing research and development for future accelerators, like here, where we would like to have more compact acceleration. If you look at the Large Hadron Collider, yes, it's a damn big beast. But why is it big? Because our magnets are just too weak. If you can build stronger magnets, we can go faster. So if you want to go really, really fast, and you would like to improve the energy at the collision of the protons, you have two parameters. We can accelerate the protons much, much faster, but if you accelerate them much, much faster, then they will slip out of the magnets because the magnets can't hold them. It's like your motorcycle. If you're on ice, you can go as fast as you want to. You will not make a circular trajectory. And the same thing is for our protons. So we need to develop new magnets which can hold. Or we do a bigger circle, like here. We can do a linear accelerator, the pink, green, and blue dots. so that we don't have any circle, so we don't have any problems in keeping the magnets, keeping the protons. We just shoot them head-head, but once they pass each other, they're gone. Or we build a 100 kilometer long accelerator, which has a bigger curvature, which means that we can drive the protons much, much faster. And that is one of the plans which we're doing. Coming back to the question on civil engineering, we know exactly our ground in this Geneva basin. Geneva is here in the center. This is Lake Geneva. This is the LHC, is the airport. We know exactly, we've drilled down already at lots of places. We know exactly how to position an accelerator tunnel underground where it's creating the least problems in terms of villages on the top, because we need to have access shafts, and of course in costs, because every access shaft, every depth costs money, and the fewer access shafts you have, and the shorter they are, the less expensive is the whole business. Pointing magnets at the sun is a telescope where you can make physics. Here is, again, this AMS experiment, which was in the day of the space shuttle. Now it's attached to the International Space Station, taking data from so-called cosmics, protons accelerated by the magnet field of the galaxy, and then crossing the experiment. So you can also make measurements there. Same mechanisms apply. Here it's a little more complicated to repair, and the communication is then going down to the standard 3 link satellites for the ISS, and then going to Houston Space Center and via a direct link to CERN's data center, where we can analyze and run the experiment. And I skipped this. If you want to come to CERN, if you want to see this, that I'm not lying, watch Angels and Demons. On the left-hand side, you see the Atlas experiment, as I've shown to you. Here in the film, you got the control room more or less at mid-level. No, that is not existing because the radiation will not be healthy for the people here running around, but this is how the movie makers in Hollywood think it should look like. This is how the Muppets think the experiment is looking like. And we have open days. This is how the CMS cavern is looking like with some visitors. We will open up again around 2026, where we shut down the whole apparatus for its next iteration. At the moment, we're just starting up, so we're in operation. Nobody can go down there. But if you want to come around 2026 or around 2026, we will have open days where we open up the site for a whole weekend. People can go underground, visit the experiments, go in the data center, play around with cryogenics, and so on. And with this, I'm a little bit over time for this one, and still open for more questions.
Well, thank you very much, Dr. Lüders. You've given a very comprehensive view of CERN and some of the details and some of the trials and tribulations that you've had to overcome to create it. So I will open the floor here to additional questions.
May I start with the chat, because we just
yes, that makes the most sense.
So yes, the SSC in Texas, a terrible decision. Money, it's all about money. This is not cheap research. Don't think that I'm driving a Porsche and I'm a millionaire. But the money in the end, the money getting in an accelerator, like the SSC, but also the LHC. The LHC is a worldwide endeavor, so the money comes from 26 different European countries, including Israel, but also from Canada, from the US, from China, from Russia in the past. This we have stopped because of obvious reasons. From India and other countries. People coming for research to CERN because we are the central hub for particle physics. The advantage here is it's international. Geneva is an international area, so you don't need to worry if you're black, white, gay, or whatever else. It is a amalgam of all the people, so you're welcome to come here. Yes, the SSC has been shut down because of political reasons. The LHC has exceeded more or less the capabilities of the SSC, but it's also another decade. The SSC was more or less conceived in 1995, while the LHC has been more or less put into operation 10 years later. One more, money. This costs money. The money is not getting in our pockets, because in the end, the money is getting into the central fund at CERN, but then it is becoming a CERN distributed subsidiary for international companies. Don't believe that we build the cryogenic systems. We develop the cryogenic systems, all the details, the control system, everything you need. But in the end, we develop this together with industry, Air Liquide, Linde. The magnets have been built by 3 consortia in Italy, France, and Germany. Part of the detector here, and this is really beautiful, part of the detector here comes from the US, from Canada. Some components come from Japan. Here's even some components of the calorimeter, which is using brass for the absorption material. It's brass. The brass is coming from unused bomb shells out of the Russian military. We should have built more experiments instead of now waging another war. But you see, this is an international endeavor for peace, and the money is going back into industry for research. Air Liquide, Linde, the German companies, the companies in the US and Canada, which is developing components. The knowledge now they gained by the development is with them. CERN is not holding any patent on any of those ones. So once more, you want to build your own accelerator, be my guest. Come to me, you need to have some money for sponsoring this, but CERN will definitely help you. Okay, people need to run. Yes, I'm sorry for that one. Other more questions?
Yes, how often are injections done to replace protons lost due to collisions?
So the injections, in principle, the cycle, as I get on my slide, is something like 10 to 20 hours of taking, and then you have 1 to 2 hours for the fill. So it's more or less on a daily basis, if not even more often. Let me just try to go back very quickly to the right graph. So here you can see this, for example. Is it a good one? No, that is not a good one. No, I don't even find it. Here we are. So this is the cycle. If you see, the preparation is at 2 o'clock, 1400. And then it's taking 1 hour to inject, to prepare, inject, ramp, and squeeze. And it's at 4 o'clock, 1600, we're starting data taking. And then this is taking really 10, 20, 30, 40 hours, depends on the components. Sometimes you get a power glitch. And if you got a power glitch, the magnet is not holding its amps. And then we dump the beam, we get rid of the beam, or the cryogenic is not stable. Or you get a thunderstorm and you might even lose the electricity from the electricity to France. Or somebody is opening an emergency exit door. We always then dump the beam and then you prepare the machine again, which takes some time, and we do another fill. So, but this is then more or less what we're now starting. Now we're starting again to commission the machine, and we will go in full production later this year. In principle, it's foreseen next week to have the first beam completely in collision. Is this answering the question?
Yes, I believe so.
Good.
The superconducting magnet wire that you mentioned earlier, what is the difference between that and just standard Litz wire?
I have no clue what a Litz wire is.
Oh, Litz wire is just basically finely spun, twisted wire used for high frequency magnetic fields.
Are they superconducting?
No, they're not generally not superconducting. They're used in things.
If you use those cables, I don't know them, but if you any other cable you take with 10,000 amps, they will melt away. Because what is the difference? What is superconducting? In principle, if you take your cable, it's a lattice of atoms, like the copper, for example. In normal cable, the electrons are going through the cable and they're hitting left and right the atoms. And every time they hit the atoms, they create some heat and the cable is heating up. This is called resistance. This is what is the Ohm's law, isn't it? The superconducting cables, the atoms are arranged in a lattice in such a way that the electrons are funneled through. They don't touch anything, which means that you can even touch the superconducting cables with 10,000 amps, and in principle, nothing will happen. At least you will not feel any resistance. You still might get a stroke, but that's something different. So you see, that is the big difference. In a superconducting cable, there's no resistance, so you can get 10,000 amps through. In a normal cable, I guess also for your radio frequency, there is still a loss in resistance. But I'm not an expert in that field, so I'm pretty sure if the cable would do at normal temperature 10,000 amps, we wouldn't do all this magic around superconducting magnets.
Fair enough. We have a question here. Would it be possible and an advantage to collide protons and antiprotons in the LHC?
That is a very, very good question. This is what the Tevatron did with protons to antiprotons. I'm not sure if I can answer the question. I'm physicist enough, but I prefer not to answer that question because I think I'm really, really thin ice here, and no, I might not be able to answer that one. I'm sorry.
All right. Are there any more questions here for Dr. Lüders?
I noticed that I didn't answer the question on the beam dump. So the beam dump is exactly now the problematic area, because we have to absorb 80 kilograms of TNT. So how the beam dump is working. So first take the 2,556 bunches, which are more or less put up as a chain. And between the first and the last bunch, there is a 4 microseconds gap. And this gap is very important. Now you got the accelerator, you got the beam, 10,000 turns a second in the LHC. So now you need to dump the beam. Somebody is toggling a switch, some emergency doors opened, electricity is gone, but electricity is slow. It's pumping with 50 hertz. We're doing 10,000 turns a second, so 50 hertz is very slow. So first turn we need is detecting that something is wrong. We need to dump the beam. Voltage is not nominal anymore, temperature is not nominal anymore. One turn to detect this. Safety systems are all laid out that they just need one turn. The second turn we need to transfer the signal to dump the beam from wherever it's detected to the one single point in the LHC where it said the point where the beam dump is. Remember point number 6? Let me see if I find it here quickly. We take it here. This one is. We take that one. So for example, somebody in Atlas here, down here is opening emergency door. You have to transfer the signal over to point number 6 where the beam dump is. This is speed of light, or this is in principle optical fiber, so it's 66% of speed of light. This takes you the second turn. The third turn is now the important one. If you look closer here, you got the beam dump. It's 2 straight sections of 300-meter long straight tunnels. And at the beginning of this tunnel, there is something like a railway switch, where you can toggle between circular trajectory of the beam and the ejection onto the dump, which is straight. So think of this as a railway switch. You do not switch a railway switch when the train is on the switch. We all agree on that one, because this will lead to disaster. So now the switch, the beam dump, has to wait until this 4 microsecond gap is coming. Where is this gap? And in the worst case, you have to wait 1 full turn before the gap is coming again. Once the gap is coming, there's a bank of 14 capacitors which can fire a magnet to switch the switch. And when the beam is then coming again, instead of seeing the trajectory for a circle, it's going straight down 300 meters. When it's going down this 300 meters straight, the beam is being blown up from this 4 millimeters to a very large size, something like 50 centimeters. And then with the 50 centimeters, the energy density is of course reduced because it's a bigger surface. And then it can be absorbed by some carbon, concrete, and I think it's lead absorber, which is then taking up the whole energy. And then it's more or less heating up the beam dump. I thought I got a picture of this one, but I might have skipped. Yeah, no, I'm sorry, I don't have a picture of that one. I have also a slide stack which is taking 3 hours, but honestly, I think your lunch break is, or you're already over time in your lunch break. So I'm sorry for that. Really apologize.
I believe there was a follow-up question whether that beam dump could then be used as a source of neutrinos.
Yes, it can. Very good question there. In principle, we get neutrinos also in the collisions. The neutrinos are nasty because the neutrinos do not leave any signature. A very, very weak signature. So out of billions of neutrinos, you might spot 1 or 2. So, but exactly this is how neutrino physics is working. And Tevatron is just preparing a neutrino lab there. What they do is they take a proton beam, they smack the proton beam onto a beam dump. It's more or less the fixed target experiment. The beam dump is conceived in such a way that it's efficient for neutrinos. Here the neutrinos are not coming out immediately, but some muons. The muons are then over time decaying into electrons. And when they decay, they emit muons, neutrinos, which can be then measured in 2 different experiments. One is the so-called nearby detector, which is still on Fermilab site in Batavia or close to Chicago. And then there is a 250 meters far away experiment, which can also see the neutrinos. We've done this at CERN, where we had also one of the accelerators, which were pointing in direction to an experiment in Italy, 700 kilometers away. So there was no tunnel, don't think there's a tunnel. But in Italy, in a cavern was an experiment, and we were adjusting our neutrino beam, because it's crossing everything, in such a way that the neutrinos were hitting this cavern. So we got also the proton beam, smacking into a target, producing muons, decaying into neutrinos then going through the Earth, not interacting at all, into the cavern in Italy, in Gran Sasso, and then being measured there. And then you can do neutrino physics with this one. That is a very, very hip topic. So if you're young and want to do physics, yeah, that is an area where you would like to go into.
All right. Well,
Ring
I
connection
wish
is the best for strong optical fiber connection as well. Don't understand. Well, maybe you want to share more. Munir? Nope. Good.
All right, then. I wish everyone to give Dr. Lüders here a round of applause. Again, he's given a very comprehensive presentation on a very complex topic. My apologies if this session ran a little over time here. Fortunately, there's so much material to cover and a fair number of questions, and they were very good questions, as Dr. Lüders has indicated. So, yes, it appears everyone here is starting to leave. Again, I apologize for going so long.
My bad, my fault. I'm sorry.
Perfectly all right. Munir was indicating for strong network connections, ring connection is most useful.
I think you might want to stay one more minute and then we'll discuss this speaking, because I still don't understand it, but I think it's my side not understand it completely. There's a question from AC.
Yes, sir. Can you hear me?
Yes, I do.
Yes, we can.
Yeah, I just asking for a strong network connection, mobile network connection for ring circle, you know, OO type ring circle, the finger ring type. It's two type of connection is if one side is collapse, not working, another side is support. So I just asking this type of ring
yes,
useful like that. Am I right, sir?
It's a good point. So in principle, you see the round tunnel. In the round tunnel, we got the so-called beam interlock system. And the beam interlock system is built out of several redundant, in both direction, redundant optical fibers, which you have to break.
Yeah. I just asking like that.
Exactly. It's working like this. It's a little more tricky because you don't want to switch off the light in the fiber. You just modulate the frequency inside, because this is then even a better method to detect that some anomaly happened. But yes, you're right.
I have a little experience about this, so I asking like that.
Yeah, okay. Completely right. Thank you very much.
Well, then, on that note, I will bid everyone a good afternoon and thank you for spending your lunch hour and a little over here on coming to this presentation. We appreciate your presence and we are grateful for your time.
Thank you very much. Enjoy your lunch.
All right, I will end the session now.